what do we have on the screen? We have a vector W. Now, there's all sorts of notation-y things, but if for any reason you've missed any of the notation or you've missed any of the notes, I know a few of you guys were absent or sick or gone or came and went and came. We'll catch you up. For right now, what is a vector? What is a vector? Going back to the very beginning of notes, just real fast.
Both direction and magnitude.
A line segment. Good. Now wait, what's confusing from the very beginning, as soon as I say line segment, and you see an arrow. In geometry, this wasn't a line segment, this was a ray. And it would go on for how long? Ever. But what is it instead?
Segment.
It's a segment. It has a beginning and an ending, which we talked about a little bit past this page, that beginning and that ending can be called like a point P to a point Q. So this one technically could have been called vector PQ with a point at the end and a point at the beginning. So it is a line segment, so then your question should be, well, why is there an arrow? Okay, all I've gotten to is line segment. Why is there an arrow? Well, hold on. Line segments have length. That's why there's magnitude, a how muchness. We talked about that over there. That magnitude, that length, a snazzy way of talking about it is putting double lines saying you are vector V or W. Vectors put little arrows on top. You are vector V. The little lines say this is your how long, your how much, your magnitude component. So just the length, like a hypotenuse, would be the magnitude, the snazzy notation. Why is the arrow there if it doesn't mean forever? What else does a vector have? Magnitude and direction. Alec, where are you? This is like your favorite quote. A line segment has both magnitude and
It's direction and
direction.
magnitude.
Directed line segment. That arrow doesn't mean forever. It means nope, 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 stopping, but pointed that way, which could be a ship leaving a port and headed that direction. It could be a person pulling on a box with a rope over their shoulder, pulling this direction. It could be all sorts of things. But a vector is a line segment beginning and could be a point P and Q. Vectors have little arrows on top of their names, whether it's a little lowercase letter or whether it's the beginning and ending initial terminal points. They have a length, which is why triangles, this is the perfect time to talk about it, because now we know how to do right triangles and log sines, log cosines helped us with what kind of triangles?
All of them.
All of them. Yeah, doesn't matter if it's right or not, but these ones too. The acute and the obtuse and all those. So it's the right time to be talking about this, because not everything's going to be a right triangle, so we have all those skills we can use. We can make triangles, and those triangles have horizontal and vertical components. So who is a vector? A directed line segment anywhere in space. You can move them around if you want. That was crazy, the whole equal vector. Like this, because we can make little like compasses for each one. Like, technically, they're all the same, even though they're in different positions. I can move vectors around as long as they keep the length and the direction the same. So we have some little things about, okay, what does it mean to be equal? You can move them around. How do you write them? What do you write above them with the arrow? What's the double line thing? Oh, it's just how long it is or how strong it is. We did some stuff like, okay, we can use distance formulas to figure out the magnitude. But these distance formulas are always going to be subtracting the x's and the y's. And so actually, this was yesterday. We said, well, there's another way to talk about a vector, not just his name from beginning to end, not just a little lowercase letter just because we want to, I don't know, call him vector W. But we can also talk about him as a movement, as going down and going over. Okay, how much down, how much over? And we put those how much quantities in these little side carets, and it's called component. Oh, he doesn't do anything. Where's this guy? Oh, this guy. Here we go. So this example, I gave a vector W, and I said, here he is, but this isn't a point. It's a destination. And if it doesn't tell you where to start, you can always just start from 0, 0 and say, whatever, I don't know. Whoever this guy's compass is, 0, 0. I can move 4 left because it's a -4 displacement. I can move 2 up, choop, choop, and then that's my ending point. There's my vector, which I can now move around wherever I want it to go. But from that, if this is how much change and how much change, can't I just throw it into Pythagorean theorem and say, oh, so u squared plus u squared square rooted is always the hypotenuse. So now we have this little baby formula, like, hey, take this guy, take that guy, square them both. Pythagorean theorem gets me magnitude. So the math isn't new, it's just how does this all work with these vector guys? And like, you wouldn't have known what this is. You would have thought it was an ordered pair if I hadn't put it in context. It does show a point, kind of, but it's an ending point, and so then I can just show, oh, a vector just connects the origin with this point. The very last thing of yesterday was this unit vector guy. Unit vector, well, unit circle has a radius of what?
1.
It's like the most fundamental. We build everything off of that. What if everything was scaled back to have a radius of 1? Every hypotenuse was equal to 1. Oh, unit vector has a length of 1. And so we saw if you have a vector that's out somewhere beyond this 1, which this one ended up being because we found his magnitude to be 2 root 5, which is, I don't know, like 4-ish, 5-ish, 6-ish. Anyway, whatever this is, it's not 1. And he said, well, you're not a unit vector. And I said, okay, we can make a unit vector by, what was the illustration I used yesterday, building into how to make a unit vector?
You have to scale it down.
Scale drawings. Take something big, write it small, like a blueprint, right? Take something big, scale it down. Scale drawings. How do we do that?
With dividing.
You like divide. Yeah, Cassie, what do you say? You can. It depends, right? Like I guess if it was a blueprint, you just need to fit it on a piece of paper or fit it on a certain like roll. I guess architects have that. They will
Divide everything by
drawing boards, but
Divide everything by the hypotenuse.
But in this context, yeah, divide everything by the biggest number is the hypotenuse because we need the hypotenuse to be 1. But scale it back, and in math, how do you scale it back? Just divide. So we figured out who he was. Wasn't 1, but if we take that vector, and I showed it over here, not that you have to. But I said, I need you to be 1. Fine, divide him by himself. You'll be 1, but I have to divide everything to scale it back proportionally. So I just say, take you, scale him back, divide by the magnitude. Take you, scale him back, divide by the magnitude. So what we didn't get to do yesterday was write a formula for unit vector. I don't think, did we? Did we write a formula for unit vector? I think we just did the example. Yeah, we just scaled back. So we're going to come back up here, everybody, and write a formula for unit vector, okay? But Alec, go ahead. What's up, bud?
So that's what I'm just like, can't you just, for the a squared plus b squared and the square root, can't you just get rid of the squares?
I wish. A lot of people think you can, and like when you're doing the math, a lot of people accidentally do. To be honest, I can show you another example of this real fast. Way back when we did trig, there was a problem, and it's in the watch out for the test tomorrow thing. 25 minus 25 sine squared. I wrote down and I made the kids highlight in regular pre-cal, like you're going to make a mistake, a lot of you, if you don't look out. Because a lot of them want to say, hey, it's 5 minus 5 sine. The square roots only go away, can only cancel out if I have a perfect square. So, if I had 5 minus 5 sine being the answer, the only way it could be the answer, like for this, and we'll come back here, is if there was 5 minus 5 sine being squared in here.
But isn't that what it is if we just take out the square root?
What's the mistake you're making? This needs to be FOILed, first, outer, inner, last. And if it's FOILed, you actually end up with 25. Yes! A negative 25 and a negative 25 sine from the outer and the inner not canceling out but joining together. And then 25 sine squared. Problem is, number 1, if you square anything, you'll never get a negative unless it's imaginary. And number 2, if you square a polynomial, you'll always have an inside term. So here's the crazy thing, Alec. This would come from that. That doesn't look near as obvious as the accidental mistake.
Yeah.
So yours is very similar. What you're seeing, you're like, hey, 2 squareds, but that addition makes all the difference because we can't cancel out a square root unless there's a single quantity squared. And to be honest, if we try to factor that, there's no way. And if it was a minus, it'd be a plus b and a minus b that aren't the same, so I can't make it that squared quantity.
Yeah.
I mean, my short answers don't kill a puppy, but that's the reason why. Good question, though, because a lot of brains keep on accidentally making that mistake. So at the end of this work, for those of you that were gone yesterday, we did an example where we said, hey, here's a vector. I have a beginning point, an ending point. We look at where the arrow is, and we take this guy and we say, oh, hey, you're the final, you're the initial. So he was my x2, x1, oh, no, sorry, x2, y2. This was my x1, y1. And we just subtracted to get that component and subtracted to get that component. We were able to then figure out, ooh, you're not 1. So then we could scale back. What we're doing is we're saying to get any unit vector of any vector v, all we have to do is take v's a and divide it by the magnitude of him, and v's b, oh, that's way too big, v's b, and scale back, divide by the magnitude as well. And that's for or with vector v starting as an a and a b. Remember, if they don't give you this, you can always find it with that little subtraction of final point minus initial point for the x's and the y's. So there's our little unit vector formula. I mean, we did it a couple times yesterday, but we never wrote down an actual, formula. Okay. So with that, now we have to say, so these little side caret dudes, they tell us, like, okay, how to move from beginning to end of a vector that could be at 0, 0, it could be somewhere else. But this is just how to move. Oh, 3 left, okay, 2 left, okay. Just how to move. Now that we know what these little side carets do, we can say, all right, well, what if we see some sort of math, like, you know what, it's time for you to do something like, I'm just going to do examples. What if you were to do something like 2v?
Then,
What would happen if I doubled this guy? 2, right? Just double him. What do you guys think? Yeah. So he would end, let me get a point out here, this is about right. He would end here instead. That makes sense, right? Like, okay, v becomes 2. Okay, double it. Think, remember these vectors, they can be forces, like how hard you're pulling. Well, if you double that, aren't you just pulling twice as hard? Okay, not twice as far, sorry, that's what I indicated, but twice as much force. But the question is, what do you guys think is going to happen inside to the components? If I double the hypotenuse, what do you think is going to happen to the rest of it? Yeah. If you scale it back, you divide everything. If you multiply, well, you multiply everything. So if I've doubled a vector, guess what else I've doubled? The components.
Yay.
I'm like, oh, so guess what?
Scaling up.
You're twice as long, and you're twice as high. Now, see, this is their weird not using x's or y's. They're using the little letter just, I don't know, to be different, I suppose. But do you guys see how it's kind of just like distribution? It's kind of like distribution. Remember, this is the vector's name. These are just kind of like, hey, it's the components. It's a number that goes with the v dude. Okay, whatever. Here's a weird one, though. What if I was to do something like negative 3v? Give me the formula first. What's going to happen to these two dudes? Yeah, triple, but what's that? Well, okay, whatever. The negative's there. Like, I just distribute, right? No big deal. What does that mean in the picture, though? It's direction. It's going to be 3 times as long, but
Does it face the other way?
it's going to face the other way. So it's going to be this. I'm probably totally slaughtering however far this is. But down here.
What's a bruh?
So it's a component.
Wait,
Oh. Do you see it?
what? I'm confused.
Well, it's this length, but it's going the opposite direction of, I just moved it down here. Going the opposite
I'm
direction.
confused.
Oh.
Where's the triangle?
Oh, I haven't drawn that yet. Good question, though. But wouldn't that take this length, and wouldn't it triple it and make it go the opposite way? Now, this was already a negative, if that was true. So what's a negative times a negative? Positive. And I'm going to go, oops, sorry, I did a bad job of that. But
I'm very confused.
Do you see that I tripled the length out?
Yeah.
And then, did you think about how the negative might switch the direction? So instead of the vector pushing this way, right?
Yeah.
It's pushing this way.
Well, why isn't the triangle on the other side of the line?
Oh, like here?
Yeah.
Think reference angles from trig. Reference angles, we'd always draw the triangle. I'm just keeping in with like the proper mathematical way of doing triangles. We always just go to the horizontal. We always just go to the horizontal.
So always the x-axis?
Yeah. Good. Or you could say the east-west line if you're doing it that way. It could be all snazzy. Now, my vector dude kind of like got in the way of my other guy, so I'm kind of moving him right now. But do you guys see that the next example is now taking two vectors and putting them together? Okay. But even though maybe the picture is a little weird, even though the whole like vector with a line thing is pretty weird, does the math seem that hard?
No.
If it's in components, it's like times 2, times -3, whatever. So what do you think is going to be true over here if all of a sudden we're supposed to add and we have vector u plus vector v? How hard do you think that math's going to be? Not hard. Because it really is just, hey, add the x's and add the y's. My brain starts to get a little confused. Yours might too when I'm using like u1, v1. I'm like, change letters, change numbers. No. u1 plus, there we go. Those are the x's, and then these are the y's. There we go. It's going to be as easy as just like the math is super easy as far as whatever, add, cool. The picture is where it gets weird. Not horrible, and maybe I can make it make sense, just weird. Because this one, it was like, make it twice as long, or make it 3 times as long, opposite direction. Okay, kind of weird. Okay, check out this one. So we have vector u, vector v. I have 2 different examples. So let me label them. We're going to make this one. Oh, yeah, he was u. I just had that one. Okay, so he's u. Oh, no, he was v. My bad. Vector v. And then here's my vector u. There we go. Here's the dealio. If I'm trying to add these two, to be honest, these could be like totally in different places. They could be acting in different ways, etc. And actually what's way more common than something being way out here in the middle of nowhere, what's more common is that it actually be right here at the origin also. I'm like, well, you're doing that, cool, I'm doing that. But the problem is, right now, if this one's working this direction, that one's working that direction. He's put on my desk, Lauren, so I pick up this one. If I'm trying to add them, what's the problem right now of trying to put them together if they're right here? Does anybody see a problem trying to put them together?
You cannot.
Yeah, I mean, he's going that way, he's going that way. Like, how do I... They're not together. They're working in totally different directions and totally different magnitudes. So the problem with how things normally appear is that they're working against each other just by not being totally together. If this one was, which it's not, if this one was this way, it'd be really easy. Vector addition would say, sweet, just put them at the end. Dun, 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 dun. But it wasn't that way, was it?
Yeah.
If it was working together, I'm just like, sweet, they add together. So if you're pushing, a friend comes along and pushes something too, right? You're working together. Force is happening in the exact same direction. No big deal. Just add both of your forces, and that's what's acting on an object. But if you're working against each other, if they're working against each other, well, okay. Do you guys remember that we can move a vector wherever we want it to be? No. Equal vectors, remember they were all drawn and they were all the same lengths and all the same angles. I can take this guy and I can move him way over here, and I can say, hey, put them together and ask yourself, what's the overall effect? Even though right here they were kind of working against each other, I can say, okay, well, I can't change him and say, yay, it's all of a sudden different. No. But I can shift him, and what we call that is going head to tail. Going head to tail. The head of one vector, like the head of a comet, is the part that's, and the tail is what's lagging behind, right? Head of one to the tail, the back end of the other. If I put them head to tail, all of a sudden I can say, okay, I know they're not working together, but I can follow the movement, the motion, the strengths, the forces, and say, what's the overall effect? You guys know how I would draw the overall effect? I say from beginning to the overall end. Oh. I just need to put them head to tail and say, hey, the overall effect is that third. It's a triangle that might not be right. Right as in with a right angle, but it's still something I should be able to solve. Adding 2 vectors is saying, or 3 vectors, or 4 vectors, or 5 vectors, is saying from the very beginning of whatever vector diagram you're looking at, ooh, that's snazzy, to the very end, what's the overall result? That's what the addition, the math, super easy. If it's in components, super easy. If it's not in components, a little bit harder, but from the very beginning to the very end, if I'm trying to put them all together, what's going on now? That can be super like, what are you doing and why? The very end of yesterday, do you remember how I talked about roller coasters briefly? I said, hey, we need to figure out what this actually means and how it actually works. Now, we can picture a loop, right? Picture a loop. If you don't like loops, I'm really sorry if you're getting like nauseous right now. But I like loops way better than like the deep drops. Deep drops, no thank you. Goliath, no. Ugh, there's no shoulder harness. I think I'm going to fall out. Maybe it's because I'm tall. Anyway, loops, I don't mind those. Some people hate the loops, get horrible headaches. Either way, a loop. It's a thing on a roller coaster. Magic Mountain tomorrow, everyone going, have fun. Go on ones with loops. Riddler, Batman, fun. Coming back. But wait. Look. You hope you can. Why couldn't you?
I'll hold your.
I lost my permission.
But maybe you get it signed and then bring it tomorrow?
Oh.
Talk to Mr. Park. Good. We all support you if you need like a waiver thing. No, not like that. That's that.
Yeah, that's
I mean like,
that's illegal, Misty.
Wait, that's illegal.
petition! We need a petition. I'll sign it. Okay, coming back. And the other one.
Chief, means they will hold my hand.
Be careful what you say. Anyway, pause. Which ones? The dudes in the cars and the loops or this weird triangle thing on the side? Which one is showing the vector addition?
The right side of the loop.
The triangles or the dudes in the cars?
The homies in the car.
Oh, left side of the.
These ones are showing the addition. Oh, check it! It's what I just showed you. If they're working together, I can just line them up and say, ha-ha. This is, okay, so wait, I see addition. I see addition here, I see addition here, I see addition here, and I see addition here. These are showing me additions. Wait, additions of what? Additions of, what does GRAV stand for?
Gravity.
Gravity. Additions of, oh, I did it too slow. Additions of gravity and, I give up. Gravity and what? What's NORM? Normal means perpendicular in that. So I have gravity, I have the normal force, net. Catching
Both of them combined.
Both of them combined, like a net profit. Everything
Net ionic
combined.
equation.
Coming back. I heard saying something. Anyway, stop. I have gravity, I have the normal force, and I have the net force. Which one do you think is the equals? Which one is the equals? Which one is the combined? Which one can I label U plus V? Good, the net. Put it all together. This guy is going from the beginning to the end. Look, from the beginning to the end. This guy is going from the beginning to the end. That's U plus V. This guy is going from the beginning to the end. That's U plus V. Yeah, this one's going from beginning. That was easy. Beginning to the end. So check it. I could call my gravity U, my normal force V. But wait a minute. Okay, this is good with the math and like, yeah, sure, whatever. I can solve that triangle and yeah, sure, whatever. I mean, if they give me stuff like lengths and angles, I can solve with log sine, log cosine. Maybe if it's a right triangle, Pythagorean theorem, Sokotoa. But does this really help you see the situation at all? If I just were to give you these, would you guys have any idea what's going on?
No.
No, you're like a triangle. But pause. What's really going on? You have guys, girls, I don't care, people, in a car. You have gravity trying to pull them where?
Down.
Straight down. You have wait, what's true about gravity in all of these situations?
Straight down.
Because that's what gravity does, right? Gravity, 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 gravity. Why are they all the exact same length?
Because they're all the same amount of gravity.
Gravity is the same constant acting on everything at once, right?
Yeah,
Okay, so they're all the same length, they're all the same direction, got it. But who's the other gravity?
The force of the thing, of the car.
What's that? No, not of the car. It's actually the force that the people in the car combined are making against the track. The normal force. Perpendicular to wherever this guy is. Perpendicular to that. See it? Perpendicular to that. Or wherever this guy is. If you want to. If you want to get deeper into physics. Perpendicular to. It's perpendicular to wherever this guy is. Or it's perpendicular to. Or it's perpendicular to. Oh, hey, perpendicular is the same direction as gravity. Oh, it's the same direction. I get it. So what's going on? It's saying combining gravity and the normal force, which in some ways, shapes, or forms are acting separately, but when you're in the car, are you feeling it together? Yeah, you're feeling it together. You're just feeling one force acting against your body. True? So you're feeling the combined. You're feeling the combined. You're feeling the combined. Even though gravity is good and all, I think I kind of want to think about both of them together to feel what I'm, or to know what I'm, or to know what force is acting on me combined. It's not physics. I shouldn't go much deeper. But long story short, this is the practical, what's actually happening. Practical, as far as seeing them working against each other, but in all reality, what's most important is combining them. And that is what vector addition does. Vector addition just says, if you can get A's and B's and A's and B's, just put them together. But if you can't, okay, fine. Start with one, head to tail, go through the other, and then ask yourself, what's the overall? And that overall, which is maybe the hypotenuse if it's a right triangle, or maybe just a third side of a triangle, might not mean much to you until it actually gets applied to some sort of vector diagram in context of forces or accelerations or all these things acting on a certain object at a certain point.
Oh, no.
But look, do you see any roller coasters?
I see.
Do you see any crazy, we have to draw triangles and we have to draw lines and arrows and people in a car and a loop and that? No. I just see numbers, don't you?
I'm scared of numbers.
Now pause. When you're writing this down, what should you be doing over every single time there's a vector?
Vector.
Mm-hmm. Is the book going to be doing it?
No.
Why? What does the book
The
do?
rebellious against it.
No, the book's doing a notation, just something you can't do. What's the book doing?
Bold.
Making them bold. Do I want you to write in bold? No. Put little arrows on top. You can't write in bold. I don't want you to write in bold. Some of you would do it. I don't want you to write in bold. Put little arrows.
Emily.
What?
I don't remember asking.
I don't remember hearing.
Is the math hard? If I have these guys in components, what happens if I say add them? You add them? That's easy. What if I say subtract them? Okay, your turn. I added them. You subtract them.
Okay.
Okay, I added them.
What?
One. Negative.
1. 2 minus 1. And negative 2, right? And then, well, to do that, shouldn't you maybe double the u?
I'm very confused.
Wait, you're confused by the numbers? Okay, hold on.
4.
If I add u plus v, what's 2 plus 1?
3.
What's 1 plus 3? Right? I'm adding the a's, I'm adding the b's.
Okay.
I'm subtracting the a's, I'm subtracting the b's. I'm just doing the math.
Okay.
See it? But now I have to do 2u minus 3v, which is going to be, okay, maybe I should do a little bit of work. 2 times, wait, I can do this in my head, I think. Can you? What's 2 times this dude? What's that going to become?
4, 2.
Yeah. Minus, what's 3 times the other dude going to be?
3, 9.
Okay, so then I'm basically combining like terms. Does this kind of make sense?
Wait.
2 times u times 2 times 2. 3 times v times 3 times 3. Now I have to do u1 v1 minus, and then u2 v2. Are you okay? Pause distributing and putting together. Okay. If I wanted you to sketch the resultant vector.
Nice.
No, I have the u's and v's. I have the u's and v's. If I wanted you to sketch the resultant vector. That's that red one that you guys just saw, that net force, if it's in context of actual like forces acting on an object at a certain point in time. You could try to do what I just modeled for you as far as, okay, head to tail, connect. You could do head to tail, and connect. Because then I would have to take the blue guy, I'd have to move him up and say, okay, so I'm from the origin, got it. But pause, even though I could move him, I didn't move him very well, I'm supposed to keep him parallel. Let's do that, and then move him. That's smart. Check it, guys. For A, didn't we get 3, 4? So that's 2. Wouldn't 3 be 1 more? Wouldn't 4 be 1 more? Do you notice I could have just graphed 3, 4 and had it without needing to think about the picture? I could have just graphed 3, 4 and been like, ha, but look it. Put them together. So wait, for letter B, couldn't I just graph 1, negative 2? I could just go over 1, which is half of 2. I could go negative 2, which would be like that twice. I could just graph it and say 1, negative 2 from 0, 0, go right 1, down 2. But couldn't I also have done u, which is that blue guy, minus v? Couldn't I have taken v? Couldn't I have made it go the opposite direction? And couldn't I have put those together? Whoa! I could have taken v minus v, made it go the opposite direction and shifted, been like u minus v. Ah, okay, left. Or I could have just graphed 1, negative 2. Either way. So this last one. We ended up with 1, negative 7. 1, oh, stink, negative 7 is going to be hard. It's like this 3 guy, the 3, 6, and a little bit more. So it's like down here. How can I get my vector diagram to be that? I have to do 3v on stink. Well, that's 1, 2, 3. Okay, so I have to go 3v. And I have to go 2u, right? Stink. I'm going to go this way. So it's 1. Double it, so I can go either direction. Okay, so I have 2u. So I have 3v, I have 2 of those u's, and I need to subtract something. Oh, okay. So it would be 2 of these u's. I just need a little more space. So 2 of these u's minus, which means flip him the opposite direction. 3 of these v's. Oops, well, my 1, negative 7 didn't work out so well, did it? There we go. Well, I guess my negative 7 was a little too extreme. Not quite as much fun.
You can add other neutrons.
There you go. But anyway, there is a way to do it. There is a way to do it with the picture, but usually the math is so much easier. There is a way to do it with the picture, but the math is usually so much easier. In physics, these would be called vector diagrams, like starting with, okay, one object, what's happening, and then getting them all in line and asking the overall force, the net force. But the nice thing is, if we can just get these component dudes, man, the math gets way more exciting. Don't worry about this for today. It's kind of like some ins and outs, some caveats of properties. Instead, let's kind of talk about one other way to do components. Because I've been saying that there's one way to do components, which is, let's write this guy as 7, 5. because starting from the origin, I would move 7 to the right and 5 up. I've been saying that, but what I haven't shown you is there's actually another way. Oh, unit vectors. Wait, we already did those. We already did those. Let's not worry about that. Let's instead, man, we did like all of this. Yeah, hold on. I just did all that way too early. I didn't realize. Okay, let's do this. There is another notation. There's another way of describing this guy. And the other way of describing this guy is instead of 7 and 5, we can also say that he's 7 in the horizontal position and 5 in the vertical position. And what that is using, I is a vector, J is, these are little baby vectors. I is just the name that we give the most basic horizontal vector, and J is a name that we can give the most basic unit vertical vector. So this one technically has 0, 1 as his components, and this one has 1, 0 as his components. This one is like the horizontal unit vector, and this one is the vertical. And this makes it look so much more complicated than it really is. Since we already talked about all that unit stuff. It's just another way of writing it. Like if you see, it's still 7 and 5, just 7 is the horizontal, we say I, 5 is the vertical, we say J. That plus just says put it all together. It's weird because you're like, wait, do I actually add it? No, it's just, okay. This is this. It's technically called linear combination form. So if we were to go over here and look at a vector W, we could use our side brackets. If we see that it ends at 4, -5 from 0, 0, we can use our side brackets. Side carets, sorry, they're not brackets. But we could also use this I, J form. And they really have the same numbers, they really have the same meaning. Just this one is called component form. And this one is putting the components into what we call a linear combination form. Combining horizontal and vertical. So they mean the same thing. They use the same numbers. We're just going to use that 4. We're just going to use that -5. Just this one kind of isn't as confusing as an ordered pair, but it almost makes it harder. So what I'm trying to show you down here is if vectors show up in a different way, don't stress out if there are I's and J's. Do the same thing you would do if they were in these little side carets. And to be honest, if you don't like the I's and J's, you could technically rewrite it into the side carets and then come back into linear combination. Because that's a 1I and a 5J. I could rewrite vector U. Or I could rewrite vector V if I wanted to be 3 and -2. So I could do it either way. So when this one says double V, it's like, okay, double that. Okay, it means double that. I could say it's just going to be 6. And I put the I, because I'm trying to do linear combinations. -4. So even with I's and J's, you still just distribute, or you still just combine like terms. And combining like terms would say add the I's. 1I, 3I, no problem. 4I. 5 and -2, no problem. 3. Unit vector, no problem. Take the A, take the B, and divide by the, well, I do need to find the magnitude, which is that little Pythagorean theorem, dude, we talked about at the beginning of class, which would be root 26. But maybe, depending on the directions, maybe they want you to do that rationalized with I's and J's instead. But never fear, it doesn't really change any of the math. It doesn't really change any of the steps. It's just a different way of writing those side carets. Okay, we've done a lot of work that you guys noticed. What did we not get to?
Word problems.
Word problems.
Thank God.
Because the one thing we haven't talked about is what if we don't have the side carets? They made everything so much easier. How do we get them if we have word problems with angles and distances? Alright, that's fine. We have all tomorrow. We have all tomorrow. Good job, guys. You need to get going and homework on the basics at the beginning. Make sure you have the basics, and then the word problems will be easier.